for, what is it? It's sort of like the Ableton line. Oh, that's it. Okay, yeah. So I think that's in Java. MIDI remote scripts is Python. So these are all, as I said, software specific. And every time you want to support a device on these library, it's usually a pretty big code base. It's usually half a dozen files, pretty big files. And they both call, function specific to interacting with the device and function specific to the application. So it's everything entangled. And so in 2017, at this very conference, it was not too far from here, it was in Saint-Etienne, we had Harry Van Haren present OpenAV controller, and I stole one of his slides there, because he had this idea of the middleman, the idea that you don't have to rewrite the interaction for every device, every protocol, for every application. You can just have one library in the middle that does the interaction, and then you can just integrate with this library. So it's great. I have to say, OpenAV was a great project, but I haven't seen any updates in a long while. It's also written in C, and I'm going to show you how my approach is specific to C++. So, yeah. So why button grids? I think they actually can do a lot of things. They look very restricted, but there's actually a lot of things you can do. So keyboards and drum pads for like finger drumming, we all know that. That's the pretty standardized practices. So are step sequencers and clip launchers. Arders does clip launcher very well these days as well. We have arrangement views. So arrangement views, routing matrices, rudimentary waveform cropper, that's all in the Deluge. So that's a self-contained grid device that is now open source as well. So it's the outlier, and I think it's the best as well. So yeah, it's very promising. I'm going to show you a little bit of the wave cropping. You can just see what it looks like there on the side. You can just take a waveform and you can actually interact with it on a very limited button grid. You can do very basic text display. You can even do basic spin boxes. There's a device called the circuit where to choose your BPM, it's also a self-contained thing. To choose your BPM, you don't have a screen. They manage to write, 60 BPM on the grid, and you can just use it as a very, very basic spin box. So they actually do a lot. Most impressive was the Zoya that I saw recently. Well, it's not that recent now, but I only heard about it recently, where you can just, on the grid, you have a representation of outputs for some synth and some inputs for some processor, and then you can just touch one output, touch one input, and you've created a cable like in Pure Data. So you have PD patching on these interfaces as well. So I'm just going to show, I'm just going to show you quickly this little video.
So a little while away yet, but we've got a lot of new features coming. Here's one of them.
I show it mainly for the accent.
So first of all, now when we are scrolling through files in the file browser, you can see the waveform of each file. These are just snares. You can see the actual waveform, the actual audio data right there. You can even zoom in on each one right down to the individual audio samples. That's not the main use of waveform view though. The main use is for editing sample start and endpoints. To illustrate this, I'm going to just quickly record a sample with my voice. Waveform. We are now looking at the actual audio data of my voice, as I just said the word waveform. Waveform. As you can see the play cursor, we can see what point it's actually at in that waveform as it plays through. We can now edit the sample start and endpoints. Start is shown here in green, end is shown in red. Start is being currently edited, as we can see by it blinking. We can move it to wherever we want, say to cut out the silence at the start there. Waveform, waveform. There's some more silence hiding between these two columns, so we'll just zoom in a little bit more. As you can see, there's lots more.
You get the idea. So there's a lot you can do with a seemingly very restricted interface. So I'll just go back to the slide, sorry. Right. So there's even much more that can be done, and the Monum is, again, a great example because it's so open-ended. You see other projects by independent artists that come up with very creative use of the Monum. I encourage you to check out these two examples. So there's a Bloom and Orca. Maybe people know Orca. It's an esoteric language, they call it. You can make some pretty interesting little sequences, and they made a hardware integration for it. So yeah, very, very far from just the basic clip launchers. They're also used to represent tangible timelines, so to give sort of a tangible appreciation to maybe timelines and tempos and time signatures that are maybe harder to just comprehend on paper or just in audio. So you get Samuel J. Hans UGS, where you can set up different sequences, and they can all have different tempos, different time signatures, and you can interact with them tactily with the device. And yeah, it's a very interesting project as well. It is no longer supported. It was more of a proof of concept, but it's great. And Beat Rosmi Superbrain. So again, same idea of different intervals, different sequences of different lengths, different tempos, and the fact that you can interact with it maybe make them easier to grasp. Just a note on Beat Rosmi. I was very lucky when I started this research because Pete Rosby and his team from Munich have actually done extensive research on button grids. Actually, when I started, I thought, well, this is done, actually. They've covered everything, so I don't know what I'm going to add, but I think I can just piggyback off a lot of the research they did, but yeah, they're great. I'm going to show some other example by Beat Rosmi, is the touch grid. So if we go a little step further, some people have tried to extend these grids. So you can see on the bottom there, of course, you add the third dimension. So that's a very big project, the Kinephone and the Soundform. It becomes a much, much bigger device, that you can't put in your backpack, you know. But Touch Grid by Beat Rosmi, I think, is a really good example of a very simple thing that you can add, and yet it makes a world of difference. Yeah, maybe I'll show it. So it has a very limited grid. Well, the video talks for itself, but it's a very limited grid, but he's added capacitive sensors along the axis. And so he shows that, okay, if you start creating different patterns, and then you try to add a play pause button or sequence list, it becomes completely crowded. So you can't work with this. So the idea is that you add pagination with the stroke of a finger along the capacitive sense. So he'll show it here. And now you swipe, and then you've used the little space in between the buttons to give you one more interaction to change a page. It's got nice little interfaces also for each type. Okay, swipe again, and then you have a new page again. And then it's, yeah. So that was, I thought, was a very simple, elegant solution to radically extend the possibilities of these devices. I'm going to show you just some honorable mentions. These are not technically grid controllers, but they sort of fall in and out of this idea of working with a grid or backlit buttons. Eli Feedsteel Impulse Curve, it's not a grid of buttons, it's a grid of light resistive sensors, light sensitive resistors, sorry. And with just a light on top of it and moving his hand, making the shadow, you have very low level motion capture, basically. And it's very expressive, and I encourage you to check it out. I think it's a very nice piece as well. And then Beat Rosmi again with COM. So these are not technically grids. This is not a matrix, but he's created these little modules of backlit button, and one module is one sequence. If you couple 2 together, you have a longer sequence and another instrument, and couple 3 and you have an even longer sequence and yet another instrument. So that was a very interesting way of using that, of making a modular instrument that you can, on the fly, you know, extend and reduce. And yeah, very interesting. Again, I invite you to check it out. So we have a few challenges. So the first thing would be supporting a wide selection of devices. So for that, we hope that we can make a device specification that are easy enough for anyone to write, or almost anyone to write, that you can't really make a mistake if you write it, so that hopefully the community can start adding support for their own device. Make it as simple as possible and as wide-ranging as possible. We need performance, so we need low compute costs, because ideally we would like to maybe connect it to embedded devices, and we don't want dealing with the grid to be, you know, cumbersome for tiny CPU, and we want it to be responsive so that it feels like a real UI. Extensibility, so yeah, again, adding more devices is important. Low resolution, so Beat Rosmi talk about the grid as a very, very low resolution touch screen. And so because it's so low resolution, you need to reduce graphical elements to their bare minimum. And you need to avoid clutter, so that's one of the challenges. Portability, ease to integrate to whatever software you want to use. And then modularity, as with the last example, you want to eventually maybe use different kinds of controllers and mix and match and create your own sort of setup easily. So as I said before, I'm involved with SCORE, so all I talk to you about for now is going to be related to SCORE. That's going to be my main use case for this little library. But for those of you who don't know SCORE, SCORE is basically an interactive sequencer. And the temporal model in SCORE is called branching, enables branching timelines. So you can see up there we have 2 different time intervals that both allow to play a different sound file. And then we have these little brackets beforehand. These are conditions. So if a certain condition is met, the first interval would be selected. If another, if not, it will be the other one. We have the little T, all the way at the top there, T there is a trigger, so it allows you to, in real time, set a different length, set a malleable length to your intervals, let it run for longer than it should. And then all the way on top, we also have transitions, so you can jump back in time with this arrow, this dotted line on top of there. So with these basic elements, you can do a lot of manipulation of your scenarios and of your processes. And then in SCORE, there's is just showing here the scenario and the sound files, but you can also have synthesis, you can have step sequencers, you can also work with shaders if you're doing audiovisual stuff. So there's a lot there, so if my thinking is if I make this library work well with SCORE and with enough features, I'll eventually have to cover all this ground and have to implement an open, okay, it's 5 minutes, an open standard. So yeah, for the approach, well, maybe I'll just show you then. I'll just skip that quickly, sorry. Yeah, I'm just going to show you quickly. So here we have SCORE, and in the settings, I'm going to show you this. We have the hardware here, and for now there's no hardware, but I've connected the launchpad that you see here. Hope everybody can see it. Okay, it's not going to topple over. And so here I can select the launchpad process. There's 2 modes, but I just select the first one. I go okay, and okay, so now you have the view of the scenario, like I showed before, and there's a very lonely little state all the way at the top there. It's just a point in time, and you can see it represented here. So in SCORE, you can take that point in time, you can move it around. Hopefully it does, yeah, move around here. You can create some more intervals like this, which are the lines where the time passes. You can see it represented here on the device. I don't know if the colors are showing well, but you can also double click somewhere and create another little state. And then you can see it represented on the device. It's very basic at the moment, right? So I've created another floating time point here. By default, it's got a little trigger on it. So displaying is all right. Things can move around, and we have a fairly smooth representation here. But the idea would be to use it as I said, as a low resolution touchscreen, so then we can interact with it. So yeah, just move it around, extend it, kind of like drag and drop as you would on your phone. Sorry. Oh, is it okay? Okay. I'll speak close to it. Okay. And then we don't want too much clutter. So here we see that we have a vertical white line. It's not showing, so yeah, really, thank you very much. So yeah, we don't have too much clutter, but only if we touch the relevant part of the scenario, then we can see the missing elements that we can then interact with. We want also to be able to create intervals by just maybe holding one and then double clicking somewhere. And now we've created a new interval, and we can move this one around as well. Another thing is we have basic transport, so we can move around this scenario that we've just shown. We can move around in every direction. We see also that we have the trigger, so when we play the scenario, we see that there are different colors representing the color coding of the different part of the scenario. If I, sorry Victor. If I play this little lonesome interval, I can see that it changes color and it becomes green when it arrives at the end. Again, it's very basic. And then I can use the stop button here to stop the playing of the scenario. I can maybe, let's see, one final thing. I'll just add a bit more here. I put a condition, and I say that this condition is never true, for example, sorry. It's a live demo. I can't create condition from the device yet, but hopefully shortly. Yeah, there it is. So let's say it's never true. And then when we play this and we will arrive to that condition, we can see that it is red here and that it will render, oh, no, that didn't work. So scratch that. Okay, so I guess that means it's the end of the demo. I can also do a bit of zooming and zooming out, but I'm starting to have artifacts, so I'm not going to show that. Thank you very much. Just to finish, well, maybe I can keep the implementation stuff relevant to if you have questions.
Exactly. Thank you very much. So we got time for maybe one or two questions. Okay, so I guess Thibaut will be available.
Yeah.
And be able to answer your questions concerning the implementation, if you're interested in that.
Do you mind if should I just go a little bit over?
Well, we also need some time, or maybe we should check, is Sven Thielen. Ah, you're right there, okay. I missed you the first time around, or maybe you were outside. So I think we should maybe call it the end of the demo, so that Sven can install his stuff on the stage. Thank you again.
Thank you. Cheers.
Hi. Okay. Then just just wait for it.
You don't need anything else. That's great.
Yeah. Okay. You can, but I included the questionnaire inside the talk, and practicing were around 15 minutes, so I think we are good in time. But you can, of course, if I elaborate too much.
If I make that gesture,
Okay,
it's all about
I know.
we need to go into the Q&A.
Yes, the next one.
Okay, that's great. Okay, second presentation this morning is by Sven Thielen, and it's about Jack Tripp, and I guess it's a kind of case study about open source, so we hear the rest from him.
Thank you, Albert, for the introduction. I'm thrilled to join you at LAC2025, despite breaking my midfoot 12 days ago, an injury requiring no immediate surgery. I couldn't miss this conference as this is my first paper presentation, and I appreciate the Linux audio community to be my primary audience. So I share that. Today we'll explore Jack Tripp's resilience through architectural evolution and collaborative governance using the phenomenon of architecture erosion in free and open source software as our lens. I started investigating this research topic during my master's thesis, supervised by Chris Schaaf, who I would have been glad to meet here in person, but maybe he's watching, and I can send some warm regards this way. And to ensure methodological transparency, the analyzed Jack Tripp versions refer to a certain historical phase in its evolution. However, architecture erosion is still a topic of current research and requires further work, especially when talking about case studies on open source softwares. My findings prompted a core question: are we conscious of software architecture and erosion? How do we evaluate architectural health in audio software? Which tools detect architectural smells? What mitigation strategies exist? This matters because technical debt affects all software, regardless of size and domain. Like an untreated injury, hidden architectural issues may not break your system today, but they can cripple it tomorrow. For this reason, I was kind of X-raying Jack Tripp to look for issues that might be masked or hidden. And to be honest, regarding my foot, I am a bit afraid that it may later become an issue if not treated at all after this conference. So what is technical debt, and how does it relate to software architecture? Imagine developing an LV2 plugin. A simple start with one module, then added GUI dependencies. The source files are represented as block, while connections illustrate dependencies. While we add the GUI, we introduce another module depending on the former and so on. Further development yields additional modules and introduces more dependencies. We eventually decide to organize the source code via a file hierarchy using folders while extending its features. And we may have to rush feature additions or need to quickly fix issues in order to make the plugin work for the next demo, for example, at the Linux Audi conference. And if we jump in time and look at the architecture after years of accumulating technical debt, in this way, we end up with a structure referred to as big ball of mud or spaghetti code due to its appearance. Software architecture must support a system in a sustainable manner by setting guidelines and managing constraints in order to avoid violations of the design. Most of the times, implementation requires trade-offs with adaptations of the architectural design or vice versa. Architecture erosion is a phenomenon that naturally occurs in software systems. It describes the situation when the intended or planned design is violated, inducing structural decay, for example. Recalling an analogy from the construction industry, erosion happens if a building is adapted or extended in a way that has not been considered in the architecture. Imagine a bungalow that is gradually extended by a second floor. As it has not been intended to carry another floor, cracks and deformation are likely to appear until the construction erodes. In a software system, this would be the moment where maintenance is cumbersome and you cannot add features without breaking it. Typical symptoms include architectural smells that indicate suboptimal decisions in architecting that might become an issue during the evolution and implementation of a software. Barbat et al. Researched possible reasons in open source software, and they regard rushed evolution, recurring changes, and a lack of developers' awareness as most prominent reasons. A rushed evolution may be characterized by an increase in smells through successive system versions. Secondly, due to recurring changes, development activities are prone to mistakes. The tertiary reason potentially stems from inexperience, inadequate architectural or business knowledge, and hobby contribution, leading to improper code or insufficient long-term commitment. Considering the environment and background of a software project, you can't leave that out. Lazar et al. Describe how small proof-of-concept programs originating in academia can become complex software. An existing tool is picked up by a PhD student and used as a research foundation. Different research objectives urge the need to extend and change the tool inconsistent with the original design decisions, leading to a software archipelago as shown in the picture. O indicates the original project over here. In this set of islands, and major extensions are designated by a capital M, while minor extensions use a lowercase m. Major extensions are introduced by new contributors such as students, postdocs, after initial developers have left the project. They add new functionality by either leveraging O's existing APIs or by adapting them, indicated by the index 1 or 2 respectively. Similarly, minor extensions represent less than moderate deviations from O and are distinguished by the intensity of drift from the original project. So that was some theory. The phenomenon of architecture erosion is entangled with the process of software development in a real-life setting and influenced by the environment and context of the software project, as we just learned. For this reason, a mixed methods case study on historical Jacktrip versions 1.1 to 1.68 has been conducted. Jacktrip is a critical case as initial Measurements imply that symptoms of erosion occur for one or more reasons, as discussed before, and its academic origin might be related. We employed software architecture recovery and analysis using Arcade Core, which is a re-implementation of Arcade, with the algorithm for comprehension-driven clustering, and investigated erosion symptoms via architectural metrics, visualizations, and detection of dependency-based smells. In addition, we interviewed 4 developers of diverse background and commitment, open questions, and a guideline guaranteed focus during the sessions, and we analyzed the transcripts using thematic analysis. JackTrip originated at Karma and is driven by the research of internet acoustics and network music performances. It builds upon Jack and Qt and has been commercialized by JackTrip Labs using geolocated server instances for connecting clients in a virtual studio room. But it can also operate in peer-to-peer mode, for example. In the timeline below, you can see that there's some periods where there weren't much development happening, and JackTrip was rather used as a tool to enable network performances. And then the evolution accelerated during the commercialization phase in the pandemic. Focusing on this period, we can track the introduction of new modules or clusters and dependencies. First let's have a look at JackTrip's architecture before the Virtual Studio feature has been integrated, version 1.53. In the visualization, source code files are represented as circles, and the dependencies appear as lines with arrows pointing to the other files which the file is dependent on. We won't go into the details of all the nodes and edges. We just use these visualizations to get an overview of what's happening to the code base from a holistic point of view. While I click through the visualizations, new clusters and introduced dependencies are marked in red and blue. After the inception of the main Virtual Studio module in version 1.6.0, it continuously introduces further dependencies and new modules. Yeah, and finally, the last visualization shows the sum of all additions contributing to the complexity of JackTrip's code base. So, is this problematic? Typical architect's answer is, it depends. We can better understand if the growing complexity impacts software principles like loose coupling and high cohesion by using metrics and smell detection. In the left-hand diagram, 2 surges of link overload smells can be noticed during the transition from version 1.53 to 1.6.0 and 1.6.1 to 1.6.2. A link overload indicates design issues where one class has too many connections to other classes. Think of it like a person trying to talk to too many people at the same time. Can't do that. And we can see the increase of link overloads with the release of version 1.6.0 and 1.6.2. Conversely, the number of dependency cycles, which is the blue line, decreases as of version 1.3.0. However, looking at the involved clusters reveals that the one and only dependency cycle who is left over includes an increasing number of clusters related to the Virtual Studio feature since its inception in version 1.6.0. So there might be something in the dependency cycle kind of attracting other code to become part of this smell. On the right-hand diagram, the architecture-to-architecture value, A to A, dips in correlation with the introduced link overload smells, here and here. On the contrary, the architectural instability continuously decreases as of version 1.3.0. This paradox highlights why JackTrip felt stable while accumulating hidden depth, and that clean metrics can mask structural decay. For this reason, we need more information to make sense out of the source code. This is a moment where you need to talk with the people knowing the software system inside out. The interviewed developers of Jacktrip perceived the evolution during the COVID-19 pandemic as rapid due to the increased public interest in solutions for remote music collaboration, which probably induced symptoms such as an increase in architectural smells. In the early commercialization period, governance ambiguity between Jacktrip Labs and the open source software project caused instability due to uncoordinated contributions. Tensions between commercial or customer-driven priorities and passion-driven engagement in the open source software driven by academia were described. However, process improvements optimized the collaboration. Tight coupling using Qt's signals and slots or redundant logic for settings management with the introduced GUIs, which resulted from Jacktrip's initial design as a CLI application, complicated modernization. A proposed solution was to decouple the core protocol into a shared library. However, framework dependencies and backward compatibility delayed realization. Foundational low latency design from the 2000s era clashed with modern needs, creating technical debt during IPv6 adoption and protocol extension, for example. Protocol modernization also stalled by a lack of specification, and Jacktrip Labs rather prioritized accessibility to promote the commercial Virtual Studio feature, sacrificing some low latency focus. And last but not least, Jacktrip is an artistic tool and research object itself. So our research reveals 3 key lessons for managing software architecture. First, proactively monitor erosion using architectural analysis. Metrics like architectural instability and smells, in addition to visualizations, provide early decay warnings. Second, take these indicators with a grain of salt. For example, a dependency cycle must not necessarily become an actual issue. And if you use the investigated Jacktrip versions, the findings are no categorical statements about the quality of the software. However, there might be hidden technical debt you are not aware of, which eventually induces issues. Third, talk to the developers for background information and to fully understand erosion causes like rushed evolution. Looking only at the metrics won't enable you to learn about the design decisions and their history in the evolution of a project. Lastly, institutionalize architectural knowledge with architecture decision records, ADRs. ADRs document trade-offs, enhance traceability, and fill critical documentation gaps like IPv6 transition strategies. At this point, I would like to know whether Jacktrip's architectural journey is unique, or do you have encountered similar challenges? That's the reason why I'm giving this talk. What is your recipe to identify and address issues like smells, and what is the state of architecture in audio software? So I think this would be kind of the question. Almost. Just one other slide, but it's like I want to present it after hearing some opinions.
So I think we can all relate to these questions. The biggest question for me is the kind of developers we get in the Linux audio community who might be well versed in all things DSP, but probably skipped their software engineering courses during studies. So it might be in the nature of the beast and the kinds of problems we tackle here. But we have many open source developers here. I see many familiar faces. So I'm sure there are some comments from projects which have been underway for a long time. Victor, how do you deal with this in C-Sound, maybe?
Yeah, actually, it would be a good idea to do similar study with us. You know, we've been going for a long time, and I think one of the one of the issues I find is that kind of the turnover of developers. We have a core group of people who contribute, but then you have people coming in and doing things. So, which puts a stress on us to curate. So what is going into the software, what isn't, and we see, for instance, that a lot of the issues that we have carrying the software forward is to try to handle the curation from in the past, that happened, things got in that maybe shouldn't have got in, so we then have to work around that. It's a bit like I actually sometimes feel it in a very minor, as I've kind of compared, to the millions of code lines that you have in the Linux kernel, but it's very similar, that we are looking at things and checking the PRs and seeing what will go and what won't go, and often you have to have a figure of one of the benevolent dictators, to carry the project forward, and I think that's probably a key, particularly if the project gets larger and larger. Someone who have the vision and the knowledge to move it forward. But I think it's a really interesting approach. What you're saying, it was actually quite new to me, and also interesting that we could inform even like software archaeology projects. Looking at different past projects that were finished and seeing how they evolved, and so we can learn lessons from there. Thanks.
Thank you.
So, any other opinions on this? Come on, guys. I see many people who run their own projects, big projects. Okay, I'm not sure who was the first, but...
Yes, I think a common pain point are extension points which are too good to extend. So often you have a very clever, very cool extension point where it's very easy to hook in. The classical example is a switch case statement. It's incredibly easy to add just another case and just another case, but after some time it's almost impossible to disentangle the maze which evolves. And often the problem is you have only one such or two such points, and everyone hooks into that point and then plays from the left pocket to the right pocket and creates with global variables and this kind of state. And it's often difficult because it doesn't cause pain. It looks clean. It doesn't cause pain. The people who are in the project have no problem navigating it because they know it inside out. And that's a very common pattern I've seen I've worked in the finance industry also in my professional career. I've seen many very old code bases, and it's a very common pattern which happens.
Thanks.
Thank you. Thank you. There it was. I was looking. I know that there was another comment up there. Sorry, I'm not that quick anymore. Maybe we can do.
Yeah, hi. So it's not related to audio, but and actually it's not a project that I've contributed to myself. But very similar kind of concerns came up when I was looking to use a project called GNU-Net, which is a peer-to-peer networking protocol, which has been going for it's quite an old project. It's been going for about like 10, 15 years. But it's very academic. So it originated in academia, and it's had a succession of like masters and probably PhD students who've contributed this and that. But unfortunately, it's just an utter mess. It's no joke that literally, even after 15 years, you cannot just download the source code, build it, and then connect to a network and do something useful. And you think, well, after 10, 15 years, like, what have you been doing? But this is a problem. Like I say, it suffered to such an extraordinary degree of this problem of people coming in and just contributing something and then going away, and no real overall purpose in the project, no real overall direction, except to serve as like a research base, a code base for almost for the purpose of doing research. And so I kind of I had altercations, discussions, animated discussions online with the GNU-net developer community, and the recommendations that I gave to them, which what I would echo here, was basically that you really need to exploit the power of saying no. So if someone comes along, like a student who has an idea of something they want to contribute, well, say, if it's not up to the standard that you would expect a high-quality software that's usable for users, then no, you can't add that to the main code base. Add it to a branch, you know, maybe do the development in a branch, but it's not going to go into mainline until it's of sufficient quality. And really, I think with that, you're going to cut out, you know, 90% of the craft that gets into many code bases. Certainly GNU-net.
Yeah. Thanks for the comment. Okay. Nice.
To add to that, there's also in the Linux audio community the issue that there's mostly only one developer working on a project, or two, so we don't run into those issues that you presented on a larger scale. And the standards, LV2 would be one example, where David's really putting the foot down. There it matters to say no. But most of the other projects are really, very few developers, and you don't run into the big mess of, mergers that you presented in for most of those. Yeah. So we're lucky.
Yeah, thanks for the comment. Okay.
Any other comments?
Okay, then, okay, sorry.
Yeah, I think I've also seen this happen even when there's not all of the merges that we've been mentioning. Just when projects branch off of each other and you end up with 4 different projects that all sort of serve the same purpose with their own specialties. Like I've seen this happen with Pure Data. First there was Pure Data, then there was like PD Extended, then there's PD Lorc, there's Per Data, and all these different projects have added their own things, and then like the other ones have taken the things that the one has added and brought it back and added it in there, and then maybe had to change it a little bit to fit how they have been doing things, and then just slowly over time all of the little like bringing different things in leads to mess in many of the different projects. So, yeah.
Yeah, thank you.
Not unheard of in commercial projects as well, I've been told. Yeah.
Yeah, just...
So I think we got a good sampling of the opinions.
Yes. I won't leave you with that, so before I close this talk, I'd like to propose the following actions. Check your architecture using tools such as Arcade Core to look at your code from the perspective of an architect. Discuss your findings to provide new insights while contributing to the body of knowledge regarding architecture erosion and its causes. Keep your documentation and specification up to date, and consider architectural decision records to transparently communicate trade-offs. Include RDRs in your version control system or wikis to maintain a history of architectural work in your software. Make architecting part of your development activities and spread the word about the erosion phenomenon to raise awareness. If you already navigate dual identity projects, such as academic commercial ones, and have evaluated governance models for priority alignment, share them within the open source community. So, thank you, despite my food. I'm grateful to share this research. May it inspire you to view your code through an architect's lens. And just as a side note, I'm looking for supervision for doing a doctorate. So if you got interested in spotting and understanding architecture erosion, let's have a talk. Enjoy the rest of LAC.
Thank you, Sven. So, our next presenter needs no introduction. And the software he will be presenting needs no introduction either. It's one of the longest running legacies in computer music, actually going back to the very beginning, to 1957. I wasn't born then. And as you know, C-Sound came out of the music programs by Max Matthews. And while they're setting up, I should maybe tell you about the title. There it is. So we have C-Sound, and we see we got some actual hardware here. You could hear it. So we're going to see C-Sound 7, which has some extended interfaces now to run on bare metal and to use all kinds of co-processing hardware like GPUs and such. And okay, Victor.
Hello,
take it
everyone.
away.
It's really good to be here after a few years of absence, and we actually have been involved in the Linux audio conference and community for many, many years, and for the conference since the very beginning. So it's great to continue our association. So the first thing I want to say is that this presentation is dedicated to Barry Verco, who sadly passed away in the last few weeks, and he actually was an open source developer before the word became more known. So his contributions are many and very influential. So, as Albert said, we're going to just give you a little context in terms of historical context. And in fact, we're going to go back all the way to 1957. So I'm going to just talk through a little bit about where we are. So this is the so-called music and paradigm, or the music and domain-specific languages. So we start with generation 0, which wasn't a programming language, but it was the first direct synthesis programs in anywhere. Anytime. So these were Music 1 and 2, well, retrospectively called Music 1 and 2, but they weren't called those. They're called the sound, whatever. And that was 1957-58. And then the first music DSL, really, for direct synthesis was developed with what we retrospectively called Music 3, but it actually was called the acoustic compiler. For 1961. Then generation 2 is the fully formed Music 4. That was called Music 4 then. They deliberately called Music 4. You can see in the manual. It's the first proper music DSL. It's a really complex system, very influential. And from there, almost all the DSLs evolved. So the third generation is what came after that. Music 5, which was Fortran, mostly Fortran, but there was a bit of assembler in it at the start. Music 360, which was written in the IBM 360 code. So that was from 1968. We'll move on in the 70s to generation 4, which you have then the Fortran encoding of Music 4B, which is Music 4BF. It's very different on the surface to Music 4, but actually a lot of the paradigm is in there. And then Music 11, which was an evolution of Music 360, because, of course, the IBM 360 was a really expensive computer. And, you know, we're talking about big mainframes in generation 3, moving on to mini computers, and PTP-11 was a really classic, very important mini computer from the 70s. Then we have generation 5, where we actually come fully into the Unix world. You have music for C music, and C sound, starting in the 1980s. So that's where we got to. Now we just talk briefly about the kind of the 40 years that we had from more or less from the first release of C sound. So it started off in as a C port of Music 11. So it was playing C port of Music 11 in 1986 for running on Unix. Very quickly it was ported to other hardware. You have transmitter hardware working, C sound working on transmitter hardware. It was ported to very quickly also to the Atari computer under the CDP project, and also to the Mac. So really interesting things. But very so in the 90s, it was the source was taken over by John Fitch at the University of Bath, and he rewrote it in ANSI C because it used to be all KNR C, and basically ported it to all sorts of environments that hardware and desktop projects, desktop OSs that could that had a C compiler. So that was version 3. Very quickly in Linux, so 1995, like less than a year, then well, maybe around a little bit over a year, maybe 13 months, 14 months, as soon as the OSS, VoxWare OSS audio was available, it was running on Linux with real-time audio. Yeah? Then in the 96, Barry developed the extended C sound, which was running on a Shark DSP. So all those things are relevant to us. I mean, I'm not talking about everything that happened, but things that are relevant to us here today. Then it was right in the early 2000s, it became available as a library and an API. It's still version 4, so one of the final iterations of version 4, which had an API and so on, but it was not re-entrant, so you couldn't run 100 C sounds at the same time. You could only run one, which is problematic, very problematic. But then we had C Sound 5, fully re-entrant library with API. And the important thing about C Sound 5 is that suddenly we moved away from the music and paradigm. It's still, it's still, you can view it as the remaining system, running system with on the music and paradigm, but it's overcoming that, becoming a modern sound and music computing system. Then later on, it was running on the one laptop per child, which is one of the first, well, actually the first sort of cheap laptop projects, which then now it's a common thing to have Raspberry Pis and so on. This was kind of a predecessor for all that. Well, we run it on supercomputers. It was running on iOS and Android in 2010. Then we have version 6 with a new parser, a new compiler. The new compiler allowed you to basically compile things on the fly, which you couldn't on C Sound 5, so it became much more flexible. Single board computers then. We started running on the Galileo, Edison, Intel chips. We built our own distribution to run on those things. It was running on the Raspberry Pi. So this is all under Linux. We had it running on the browser with Pinnacle, which was a predecessor to the kind of predecessors to the Web Audio API. And then Web Audio came along, so it was running on that. Was running on GPUs, part of it, as a co-processor, 2014. Then we also, on the web space, we moved on to WASM. So we actually, because Pinnacle was dead then, and Audio Worklets in 2017. And we ported it to the Bella hardware, real-time sort of intense hardware. So that was a little bit of history. And before we move on to talking about the actual boards, just talk about a little bit of the kind of the 3 levels of interaction that we have in C-Sound that we can think users will interact with it. At the top level, we have what we call the high level, and C-Sound is used in apps, plugins, games, VR, in our hardware systems, etc. And most people who are using know that they're using C-Sound, so just using the software through whatever interfaces that have been designed. So that's kind of the higher level of approach. Then you have the middle level, which is the common thing. People programming in the C-Sound language, using IDEs, scripting languages, domain-specific programming, and so on. That's kind of the traditional way. That's where C-Sound came from. And then we have the low level, which is Audio API level programming, implementation languages, and this kind of development-oriented work, which is kind of thing we're doing here, we're showing here. Now, this might surprise many people that there's, in 2019, we knew that there were at least 250,000 users of that because we had stats from downloads and of applications and plugins and stuff. But today, it far exceeds that. So I don't know, we don't have stats for that, but that's at least that amount of users that we have. So most don't know that we're using C-Sound. Then you have, it decreases significantly to less than 5,000 users of the language itself. But that's what you expect, because it is like kind of very specific use. And when we go down to maybe developers, you have maybe less than 50 developers that do everything that there. So when we're looking at that, it makes sense for us driving the project to think of things that will have a high impact on the top level, and that's stemming from the low level, trying to push up the stack. But we still, want more people involved in just using the language. Okay, so a little bit of bare metal now. So there's actually 2 bare metal devices I will show today. But in order to get those running, there's a number of constraints. The reason I got into bare metal is actually due to Ian and Romain, because back in 2018, I was invited to come over to Lyon to a workshop, and there were plenty of bare metal people there. And I felt a little bit sorry that we couldn't run C-Sound on bare metal. We had to have an operating system. So I got back thinking, oh, let's try to do it. So bare metal is basically defined like as a SOCs, really single board computers, like this thing here. No operating system, of course. Processor limitations, but not that many. I mean, actually, you can run stuff in it. FPU may not be present. Thankfully, these have FPUs, and so we don't need to worry about that. There are memory limitations, easy access to connecting hardware, C and C++ toolchain generally available, which is what we need, really. And everything else we can work around it. Limited set of debugging tools, so we might be playing in the dark, when we're developing, but we find ways around it. So how did we go about porting C-Sound? Well, there's no dynamic loading, so, but thankfully, back in 2010, phones didn't have dynamic loading as well, so when we had to run C-Sound on iPhone, we just had to get away with pushing everything into a big static library, and it worked. So we have ways to build C-Sound without dynamic loading. So it's a static loop C-Sound. No file system. Yeah, that's a problem for C-Sound. So we, not big problem in terms, for the very fact that it was hard to access files on right beginning on iOS. It was very locked down and so on. So we moved any temporary files, anything that we need to do into core files, so we didn't have any really file system dependencies from that perspective. But we had this big lib sound file dependency. So we removed that. Sound file API access, then we developed after that. We just put like a backend so that we can actually add sound files if we can access files. Limited on sock heap, that's a problem. So we developed our own custom malloc. We mapped the heap to external memory. No networking thread. Networking is kind of thing. Threading is problematic. So we just removed stuff. So this is the first environmental implementation. Now we have a month to talk about it.
Hello, everyone. Yeah, so the first bare metal implementation for C-Sound was with the DAISY board, which is by a company called Electrosmith. It's built around the STM32 microcontroller. It's a very common microcontroller in audio. A lot of devices like Focusrite interfaces and stuff have these, and a lot of audio devices have this. So the Electrosmith made a platform that made it conducive to audio programming, and especially for maker projects and hobby projects as well. So they take care of all the low-level details and provide very easy access to it, and audio I/O, USB communication, UART, sensors, all of that is taken care of by DAISY. Generally, the programming is done with C++ or an Arduino or PD or Max MSP Gen. But now we added the C-Sound support as well. There are a few constraints with this as well, which we had to deal with. The onboard flash storage space for the programs is quite limited, so we had to put it on the QSPI external flash, which is there on the DAISY board. It's quite easy to do that as well. And then there's also quite limited internal memory on the microcontroller, but the board has an option of getting external SDRAM of 64 MB. So we just moved the custom allocator and the heap to that. And then, yeah, so we made the firmware for this with the C-Sound API with C++, using also the DAISY hardware library to integrate with the board. And so C-Sound is compiled into libcsound.a as static library, and which is for the STM32 hardware. We just use the ARM toolchain because this has the ARM Cortex M7. So we use the ARM toolchain to cross-compile for that. And the static library is linked to by the program. And it basically, we run C-Sound in the audio callback that is provided by libDAISY for that. And then we made an interface as well to use the sensors, use MIDI and things like that. And it's inspired by the interface that was already present with C-Sound for Bella. So the analog inputs are connected with the C-Sound software bus. So there's an opcode in C-Sound. You use chan, get, ch, and get, and you just give the assigned names like analog 0, analog 1, and you can read your sensor values within C-Sound from that. And then we made a custom opcode for digital inputs, buttons, on and off, things like that, which has this signature. And we connected MIDI over UART or USB, which is both supported by DAISY. We used the MIDI backend module of C-Sound for that. And there's also logging from the DAISY. We could connect that to the message callback of C-Sound as well. So all of this is supported, and basically the user can interact just with C-Sound pretty seamlessly. And There are example projects on the C-Sound GitHub. There's also, the support is being added to the Cabbage IDE, which is a very common IDE, especially for plugins and VSTs with C-Sound. So Rory Walsh is adding support for DAISY projects in that as well. Yeah.
Okay, so we're going to quickly move on to the co-processing part of it. So the first thing I want to talk about is something that has actually been in place for a while now, but never spoke about it before. We haven't had LACs for a while. So it's using the Open Computing Language, which is for heterogeneous computing. Is a programming standard for parallel concurrent processing. It's cross-platform. Although support is uneven, as you've seen if we play the example, supports heterogeneous computing, so you can basically do device-agnostic parallel computing, and it's designed for hardware acceleration. So we can offload processing into that. Allows both task and data parallelism, which is really a plus. We can design functions and opcodes around that. And it's Kata-C and C++ API, which is good, so you don't need to do Objective-C like in the Mac and start shaking. It's a computing kernel-based design, which is the standard way for these things. You the OpenCL languages for kernel programming, and then you have C and C++ for control. And it's GIT compiled, which is a very important thing, because then you can embed it in your program. So we have some OpenCL codes. We have sort of parallel DFT. So it's basically Radix to FFT. Because actually OpenCL doesn't, if you're programming CUDA, all those things come with the programming library. OpenCL, there might be implementations, but you might have to find it. And so you may as well roll your own and do something that's specific for your program. So that's what we did. And we implemented the parallel time-varying and partition convolution. So time-varying convolution is an interesting application for it, which for really large convolution filters, it really makes a big difference. So combines task and the data parallelism, supports exceptionally long filter sizes. So when we're talking about filters that can be minutes, like an hour-long filter, which is interesting. GIT compiled kernels. So we have, so we expose that in C-Sound, so you can write your kernel and run it. So if you want to do your own custom parallel processing, you can do that. And then we have FPGAs, which is a different type of co-processing.
Yeah, so we have FPGAs as well, so field programmable gate arrays. They are chips where you can program the hardware as well. So they have programmable logic units, and you program the actual hardware, not only the software. And they are usually packaged as a SoC with a CPU core or multi-core CPU with on the same chip as the programmable logic or the FPGA part. So dividing the tasks between the two is a key aspect of FPGA programming, FPGA SoC programming. And some benefits of FPGA are they allow a lot of parallelism. They can do ultra low latency and high sample rates, sample by sample processing. It's quite powerful for audio processing tasks. And yeah, they have large throughput, and they can do computationally intensive tasks quite easily. So they're quite helpful for audio. But they are generally difficult to program, and they require low-level hardware knowledge. So that can be a challenge in the audio community. But there is HLS tools, which is high-level synthesis tools, where you can convert C++ specifications into FPGA hardware. But that also has a steep learning curve. So managing to get C-Sound on FPGA makes it even more accessible in a way. So what we have done is basically there is the CPU part and the FPGA part, we run bare metal C sound, very similar to how it ran on the Daisy. We run the bare metal C sound on the CPU part. So the Daisy had a Cortex M7. This has dual core Cortex A9, the one we are using for experimentation, which is the Xilinx Zinc 7000. So we run the C sound on the Cortex, the ARM CPU, and we made ports of C sound opcodes to run on the FPGA part for accelerated hardware processing. So this is the kind of the structure we have for interfacing with the audio in and out of the board, and then we send the audio for processing to the custom hardware. Yeah, so we'll go on to demos now. Yeah. So can we turn this up? So this is running on the Zybo Z720 board. It has the Xilinx Zinc 7000 FPGA. So it's a simple generative piece. All the generative and randomization and the synthesis is happening on the Cortex M7, the CPU, and then the reverb processing is done on the FPGA. So the reverb is a feedback delay network, reverb SC, which is an opcode of C sound. So we just ported that to the FPGA part, and we can interface directly from C sound files with custom opcodes. We call them FPGA out, FPGA in, to just send the audio for processing to the FPGA and back into C sound. So it's like a generative piece running real time between the CPU and the FPGA part.
We can do pretty much what we do on the Daisy, we can do in the other one. So if we can run MIDI and run C sound as we run there. It was just that we thought it was a nicer example to do a generative one. But we can show the Daisy now.
Just do a quick switch over.
Yeah. So the Daisy is called a Daisy pod, which is kind of board with this mounted on. But you can just have this. I just have this in my house. So you can just breadboard it. It has audio, media, everything in it. And you can just put a few pieces, little bits of circuit around, and you can run it. And this is, well, play it. This is a kind of a 8-voice virtual analog synth. Ultra low latency and control, video controls, all sorts of things. But you can also, if you have, you can do analog and digital controls over on the board as well if you want. So like very easy for product development. You can do sort of Eurorack boards. I mean, Cezanne already runs on Eurorack. There's some products, for that, but we can also now, develop, have a fully open source development with these things. So it's really nice and actually works very well. I mean, what we aim to say really here is that it poses very kind of a low barriers to development of that kind of hardware stuff, because the Cezanne language is one of the simplest languages to learn, and we're trying to also, with the evolution of the parser, so to make even easier to use it, and so that's our aim here, to have people working on the lower level and having loads more users up in the top level. Maybe we can switch to, so I have another one, a demo here, which I don't know whether it's going to work because it depends on my microphone here on the Mac, but we'll try. We might have feedback, but. So this is OpenCL time varying convolution. And we'll see. Have we got sound? So we'll just put it up there. Let's see. Yeah, but just showing you, it's running on the. Actually, this is running on the CPU because the people at the lovely people at Apple don't want to use OpenCL anymore, so they only have drivers for the CPU. They don't let you touch the GPU in this one. But in the Intel with Intel hardware, you can run on the CPU and on the GPU and the Macs as well. So. Anyway, sorry, it wasn't a great example, but I really need a dedicated microphone away from the speakers. So, right, okay, let's finish it off now. I'll just take it off here. Okay. Okay, so just a few conclusions. Our aim to, right back in 2018 when I came here was, C-Sound is not actually running everywhere. We should really look at the bare metal hardware. So now I'd say we're very close to running everywhere. We can see C-Sound, and one thing that I want to make sure the message, even more than the message about the stuff that we're doing, is that C-Sound has to be understood as two things, both as a ship of Thesaurus, which is, the software that was released right back in '88, and even Music 11 stuff and Music 360 stuff as well can be run on C-Sound. So we're preserving all this wealth of music has existed all the way back, and that's absolutely an important thing for us. It's a software that, when you look at the code base, very few lines of code from 1986 or 1988. I have actually the code base from 1988, and if it's interesting to compare. Very few lines of code survive. So everything has been replaced, but it can still be the same software. But it is a modern sound and music computing system, and that's what we did with C-Sound 5 way back 20 years ago. And then with the emergence of Sound 7, we run basically on all classes of computing platforms. It's really presented widely in audio processing applications from desktop, embedded, mobile devices, games, stuff. So it runs on, they're talking about Godot yesterday here with C-Sound, runs on Godot, runs on Unity, runs on Unreal Engine, whatever that is, and middleware, stuff like that, Fmod, and whatever it is. And the bare metal stuff opens up new opportunities for us. And co-processing is really an area of active research that is well supported with C-Sound. So all that kind of research into parallel processing can be done with C-Sound as well. And FPGA devices are really interesting stuff and offer good potential for future developments. Just one final thing, a plug for coming up in 2026. We have not the first C-Sound book, but the volume 2, okay, and containing all this stuff about bare metal and a lot more, mostly on the kind of development side. Right, thank you very much.
So now it's the coffee break. I have to look at Romain because he told me to be very strict. But maybe one very brief question over there.
Very cool achievements, thanks. Very quick, did you notice noticeable improvement in terms of latency when you're using the MIDI controller on the Daisy Seed via bare metal compared to a OS-based approach?
Maybe I'll just answer. I didn't, but there is so because you can run, particularly on OS 10, like Mac OS, whatever, you can run with very small buffers. So really, it's like in the 1-2 milliseconds sort of range. So kind of, you you can get close to that. But there, we measured, and it's definitely very low. In the Bella, supposedly you can run down to 2 samples as well. And we have measured that on the Bella, and compared to that, it's really low latency. But I tell you, for me, one of the big advantages really of running it in there is that you can, it's just this instead of that, But you can say.
Yeah, in terms of MIDI, it's probably because we can run smaller buffer sizes and smaller case amps of C-Sound on OS as well. It's not much difference. Audio processing latency is very much better on the FPGA for sure. But
Okay.
MIDI is pretty much similar.
Thanks.
Thank you.
Yeah, so coffee break time, and we make sure to return for the second session.
Just a quick detail about the program. So it says that the next session will end at 12:15. We're going to save an extra 15 minutes after that to have an open discussion on who would potentially like to organize Linux Audio Conference next year. Okay. So yeah, like we think it's good to have that. So stick around after 12:15 so that we can talk a little bit about that. Thank you.